The topic of this lecture is kernel methods and support vector machines. My name is Johan Hagelbeck and I'm a senior lecturer at Linnaeus University. In this lecture we will cover the linear kernel classifier that forms the basis for more advanced kernel method classifiers, which in turn is an essential part of a very advanced and powerful classifier support vector machine, usually abbreviated SVM. In the lecture we will use the flame dataset as example. The flame dataset is a generated dataset with two numerical attributes x and y and two categories 0 and 1 and contains 240 training examples. It's a toy problem, it's not a real-world dataset. And if we plot the dataset, it looks like this. So we have the two categories blue and red, and we have an interesting boundary between the two categories. And part of the dataset looks like this, so we have the x and y attribute as double values and then a class attribute 0 or 1. So let's start with a linear kernel classifier. It works like this. We calculate a center point for each category by calculating the average of each attribute value for all training examples belonging to that category. And when classifying a new example, the category of the closest center point is returned. And Euclidean distance is commonly used as distance measure. So we use Pythagoras' theorem to calculate the Euclidean distance by first taking the difference between the first attribute of the example minus the center points and square it plus the second attribute of the example minus the second attribute of the center point and square it and then take the square root. And then we get the distance between the example and each center point, and we see which center point is closest to the example. And if we train and test the model on the flame dataset, we get the following result. If we use the whole dataset for both training and testing, we get an accuracy of 87.50%, and if we use tenfold cross-validation, we get an accuracy of 85.83%. We can use another measure of closeness based on vectors and dot products. A vector consists of magnitude and direction and is usually drawn as an arrow in a plane as shown in the figure. And a vector is defined by its ending point. In the example, x is 2 and y is 3, and vectors in 3D space then consist of an x, y and z value, and we can even use higher dimensions. The dot product is a single numerical value calculated as the sum of the products between each value in the first vector and the corresponding value in the second vector. So we take the first attribute of vector 0 multiplied by the first attribute of vector 1 plus the second attribute of vector 0 multiplied by the second attribute of vector 1, and then we continue to iterate over all attributes, and we get the dot product a single numerical value. And the dot product has some interesting meaning. It's equal to the length of the two vectors multiplied together multiplied by the cosine of the angle between the two vectors. And this has an important implication. If the angle is greater than 90 degrees, the dot product will be negative. If the angle is between 0 to 90 degrees, the dot product will be positive. And how can we use this to calculate closeness? Assume we have two center points, C0 and C1. We define a new vector C0, C1 as the vector between C0 and C1. And we calculate A as the middle point between C0 and C1 by calculating C1 minus C0 divided by 2, as shown in the figure. And if we want to classify a new example x1 located as shown in the figure, we define a vector x1a going from x1 to a. Assume that the angle between the vectors c0, c1 and x1a is 45 degrees, and this is less than 90 degrees, therefore the dot product is positive, and the sign tells us that x1 is closer to c0 than c1, which we can see in the figure. If we have another example x2 located as shown in the figure, assume that the angle between c0, c1 and x2a is 135 degrees, and this is more than 90 degrees, therefore the dot product is negative. The sign then tells us that x2 is closer to C0 than C1 than C0, as we can see in the figure. And the formula for finding the category is the sign of x minus a dot C1 minus C0. And since a is calculated as C1 minus C0 divided by 2, we can then say that the formula for finding the category is the sign of x minus C1 minus C0 divided by 2 dot C1 minus C0. And this can be simplified to that the category equals the sign of x dot C0 minus x dot C1 plus C1 dot C1 minus C0 dot C0 divided by 2. And if we train and test the model on the flame dataset using the dot product for closeness instead of Euclidean distance, we get the following result. The accuracy, if we use the whole dataset for training and testing, is 87.50%, and the accuracy for tenfold cross-validation is 85.83%, and it's actually equal to the result we got when using Euclidean distance. Even if we tested on the same data as we trained the classifier, the accuracy was rather low. Only 87.50% of the known training examples were correctly classified. And this is because the classifier only finds a dividing line between the two categories. And if there isn't a straight line that can separate the two categories, the classifier will not be very accurate. And if we look at the flame dataset, we see that we cannot in any way put a straight line that completely separates the two categories. So we'll always get a slightly worse result. We cannot get a perfect result of 100%. And we can even have worse examples. If we have a dataset that looks like this, it's really difficult to place. We have nowhere to place the straight line to divide the categories. So if we have a dataset that looks like this, where would we place the average points? And it turns out that they will be placed at almost the exact same location. So linear classifier is therefore unable to distinguish between the two categories, and we will get a result around 50% in accuracy. To solve this, we need to move on to a more advanced kernel classifier. And the whole idea behind this is data transformation. So let's see what happens if we square every x and y value in the dataset. A point at -1, 2 in xy space will now be at 1, 4 in the x2, y2 space. And if we do this for all data points and plot them again, the dataset will look like this. So now we have a clear separation between the blue category and the red category. So all examples belonging to the blue category is now moved to the upper left corner, and the other is, the red is in the center, the diagonal. And it's now possible to find a straight line dividing the two categories as shown in the figure. So if we can find a transformation to a space where the data can be divided by a straight line, we can use the linear classifier on the transformed data. The problem is that in many real-world datasets, it can be very difficult to find the right transformation. Simply calculating the square of each value doesn't work for all datasets. It doesn't work for the flame dataset, for example. The classifier must find the unique transformation for each dataset. And searching for the right transformation is usually not possible. There's an endless number of possible transformations, and testing them all takes too long time. Luckily, we have something called the Kernel Trick, and it works on any algorithm that uses dot products for closeness, so that's why we needed a dot product based closeness instead of Euclidean distance. So it includes our linear classifier if we use dot products for closeness. We can replace the dot product function with a new function that returns what the dot product would have been if the data had first been transformed to a higher dimensional space. In practice, there are only a few transformations used, and the probably most common one is the radial-basis function. Radial-basis function is similar to the dot product in that it takes two vectors as parameters and returns a value. It's however not linear and therefore can divide more complex spaces. And the RBF function looks like this. So e raised to minus gamma and the sum of the squared distance between the two vectors. And if we look at the RBF in code, we first find the square distance between the instances I1 and I2, and then calculate the RBF value as e raised to minus gamma multiplied by the square distance. Now we need a function that calculates the distances from the average points in the transformed space. And this is actually not possible to do since we don't know the locations of the points in the transformed space. And this is where the kernel trick comes in, because averaging a set of vectors and taking the dot product of the average with vector A gives the same result as averaging the dot products of vector A with every vector in the set. So instead of calculating the dot product between example X and the average for each category, we can calculate the radial-basis function between X and every other example belonging to the category and then average the result. So if we look at this in the code, we first define some variables, then we iterate over all training instances and calculate the RBF values. So for all instances in the training dataset, we sum the RBF values for all examples belonging to category C0, and we do the same for all examples belonging to category C1, and then we calculate the Y value. The Y value is 1 divided by count 0 multiplied by sum 0 minus 1 divided by count 1 multiplied by sum 1 plus an offset value, which we will return to soon. And then we can simply check the sign for the result if Y is above 0 when we classify it as category C0, otherwise we categorize it as C1. And the algorithm uses an offset value, and calculating this can be quite time consuming, so we should calculate it once during the training step and feed it to the classify step each time we want to classify a new example. And the code for calculating the offset value looks like this. So we define two lists, L0 and L1, and we simply divide the training set so we have two sets, one with all examples belonging to category 0 and one belonging to category 1. And then we calculate the RBF values for category C0 by simply iterate over all training examples belonging to category 0 and then calculate the RBF values between all combinations. And we do the same for category 1, where we iterate over all training examples belonging to category 1 and we calculate the RBF value for all combinations. And last, we calculate the offset value as 1 divided by the square size of all examples belonging to category 1 multiplied by sum 1 minus 1 divided by the size of all instances belonging to category 0 and square it multiplied by sum 0. And if we implement this, we have a non-linear kernel classifier, and it can divide categories that are not linearly separable. So how good is it? If we train and test the RBF classifier on the Flame dataset, we get the following result. The accuracy when we use the whole dataset for both training and testing is 95.83%, and the accuracy on tenfold cross-validation is 88.33%. So it's quite much better than before. The classifier still uses binary classification. We only support having two categories, and the multiclass problem, if we have more than two categories, must then be reduced to a number of multiple binary classification problems, and we then need a strategy to decide which binary combinations that wins. We will not dig further into this in this lecture. So now we know how the kernel method classifiers works, and we'll move on to support vector machines. Consider the following data. We have two categories, green and red, and we try to find a dividing line between the center points for the two categories, and it will be placed approximately where the red line is placed in the figure. So the line in the figure is dividing the averages, the center points of the two categories. And one example here, a green example, is misclassified since it is on the wrong side of a dividing line. And in this example, most training examples are very far away from the line and is therefore not relevant for classification. And this can be a problem for both a linear or a nonlinear kernel method classifier. And to solve this, we must use a support vector machine. And this works by finding the line that is as far away as possible from each of the categories, and this line is called the maximum margin hyperplane. And that is placed approximately as shown in the figure here. That's the maximum margin hyperplane. And conceptually, we find the maximum margin hyperplane by drawing imaginary lines between all examples of a category, and we repeat for all categories, and the outer lines are called the convex hulls, and they are defined as the tightest polygon enclosing the examples in a category, and the hyperplane is placed exactly between the convex hulls of the two categories. So if we have two categories, red and green, as shown here, we draw the dotted lines, that's the imaginary lines between all examples belonging to a category. And now we can find the convex hulls as the outer lines enclosing a category. And then we find the shortest line between the hulls, as shown here, the dotted line. And when we place the hyperplane exactly in the middle between the hulls. And as can be seen in the figure, we don't need all examples to define the hyperplane. We only need the closest training examples for each category, and these are called the support vectors. So going back to the example, the only training examples we actually need is the one closest to the hyperplane, one green and two red. And in the first example we need four support vectors, two green and two red, and then we can place a maximum margin hyperplane. All our training examples aren't needed. And algorithms for finding the maximum margin hyperplane effectively are very complex, and in this course we will only learn how to use a very common library for support vector machines called libsvm. libsvm is also used internally in Weka for Weka's SVM support. So the first thing to do in the training step is to convert the dataset to the data structures used by libsvm. And this is Java code for how to do that. It's a slightly unconventional way of using the libsvm. It's a bit tricky before you get used to it. So first we need to define an SVM problem, and the problem.y is an array of doubles with a size of the training dataset. The problem.l is the size of a training dataset, and the problem.x is a matrix of SVM node with a number of rows equals to the number of training examples and the number of columns equal to the number of attributes we have. and here we write -1 because we counted the class value as an attribute. And then we iterate over all instances in the training data, and we get the attributes as a double array, and the problem.x at position y, that's the row for current training example, is a new SVM node with the size of the number of attributes. And then we iterate over all attributes. In the example, we create a new SVM node and set some values. The index equals to the attribute index. The value is the attribute value, and the problem.x I, that's the row, it's the training example we are currently at, and a is the attribute number, is the new SVM node. And then the problem.y at row I is the class value for the current training example. So when we've converted the data, training the model is rather simple. So we create a new SVM parameter, and it turns out that SVM parameters are quite sensitive. If we give wrong parameters, we will get a very bad result from a classifier. But these are some parameters that work fairly well and works quite well for our example. And we can see that we have a RBF Radial-basis function as a kernel type. When we want to classify a new example, we also need to convert the data from our representation to the libsvm representation. So we create a new array of SVM nodes, and then we create a new SVM node for each attribute of a training example. Node.index is the attribute index, node.value is the attribute value, and we set the node to the correct position in the SVM node array. And if we classify a new example, we create a double array called probability estimates with the length of a number of classes, and then we use the SVM predict probability, the trained model, that's the model we trained in the training step, and the nodes which we created here, the nodes for the attributes, and then the probability estimates array, and then we return a new result which is the category returned from the SVM predict probability. And the probability estimates is the probability for the instance belonging to each category. So we can see the probability for it belonging to other categories, not just the highest probability which is returned by the method. And if we train and test the model on the flame dataset, we will get the following result. The accuracy on the whole dataset is 99.58%, and the accuracy using tenfold cross-validation is 98.33%. So it's the best result so far. Support vector machines are very powerful classifiers which have been successfully used for a number of complex tasks, such as classifying facial expressions, detecting intruders using datasets from the military, predicting the structure of proteins from our DNA sequences, handwriting recognition, etc. Finding good parameters can, however, be tricky, and using wrong parameters can result in very bad accuracy. And which parameters to use depends on the dataset, so we have to test bit by trial and error to find good parameter settings. Weka uses libsvm internally for its SVM classifier, and the library is not included by default in the Weka package, so you need to install it in the Weka package manager. So we open the package manager and we search for libsvm, and we get two results, the liblinear and the libsvm, and you can install both while you are doing And once we have installed it, we can use the SVM classifier on the flame dataset, and we get an accuracy of 99.58% on the flame dataset using cross-validation. R also supports SVM, and it's part of the machine learning package Carrot, which we used in a previous lecture. And R uses CSV format, comma-separated values with or without header for its dataset. The RBF format is only used by Weka. So the R script looks like this. So we need to load the Carrot machine learning library, read the datasets into the variable dataset by read.csv method, and then define the path to the dataset, and we set up tenfold cross-validation. So the control is CV, and we use 10 folds, and the metric we want to use is accuracy. And then we train the model. We set a seed to the randomizer, and we train the model into the variable SVM, and we define the class we want to categorize. It should be class here. Actually, species are not wrong. I forgot to change it. And we specify the dataset. And the method is the SVM radial. It's support vector machine with Radial-basis functions. And we have a metric and the control to use. And then we print the result by printing the SVM variable. And we get a similar result as in Weka. The best result was 99.58%, as shown below here on the 240 training examples. So that was all I had to say about kernel methods and support vector machines. Thanks for listening.